So this section is on a really critical idea called the mean value theorem. The book just calls this the mean value theorem for derivatives. There's kind of an equivalent for something that we'll cover later on, but some interesting ideas. And it starts off with an idea called Rolle's theorem, and then we kind of tweak that just a little bit. So here's what the mean value theorem does. It relates the average rate of change to the derivative. So it's relating the slope of the secant, which is an average rate of change, to the instantaneous rate of change. So it relates the average rate of change to the instantaneous rate of change. Slope of the secant to the slope of the tangent at a particular point. But in order to understand the mean value theorem, we're going to start with a simple example called Rolle's theorem. And we're going to start off with this formula for the average rate of change between 2 points A and B. So it's the difference between the function values over the difference between the x coordinates, just plain old slope formula. And then what we do is, I've got a picture off to the side here. Let's suppose that on the interval from A to B, the closed interval from A to B, let's suppose that the function value at A is exactly the same as the function value at B. So if I come over here and put the point right here, and I can compute the average rate of change, since those two function values are the same, the average rate of change between there would be 0. Because if I had f of b and f of a that were the same on the top here, I'd have a 0 in the numerator. Okay? Does that make sense? So f of b minus f of a over b minus a. Since these two are the same, that's going to be a 0 over b minus a, so the answer there is going to be 0. All right? Now, if we have a nice, smooth, continuous curve that connects points A and B on that particular function, then there happens to be a point right up here. So we've got positive slopes here and negative slopes here. But right about right here, right at that point, which I'm going to drop this down here, and I'm going to call that point C, right at that point, the derivative equals 0, because the slope of this line is 0. That means the derivative at that particular point is 0. So that's Rolle's theorem in a nutshell. So Rolle's theorem says this. If f is continuous on the closed interval, okay, so it's got to be continuous on a closed interval, and differentiable on the interior of that interval. So in other words, it's got a derivative everywhere except for maybe the endpoints. Doesn't have to be differentiable at the endpoints. Okay? And if f of a is equal to f of b. So at the two endpoints, the function value is exactly the same as we've got in the diagram. Then Rolle's theorem guarantees there's at least one number c in that interval from a to b where f prime of c is equal to 0. So we're guaranteed if the function values are the same, the average rate of change would be 0. There's got to be a place where the derivative equals 0. So if the average rate of change over the whole interval from a to b is 0, there's got to be a place where the derivative equals 0. Or in other words, where the instantaneous rate of change equals the average rate of change. Okay? So if the slope between these two endpoints is 0, there's got to be a point where the derivative is 0, is it in a nutshell. Now, Rolle's theorem only guarantees the existence of one point. Could there be more than one point? Sure there could. I could come up here and I could draw another example. I could draw a function that does this. Starts and ends at exactly the same function value. Average rate of change would be 0. But in this case, there would actually be 3 different places where the derivative would equal 0. Okay? All right. So let's do a couple problems. Now, I modified these as I was looking at these notes. I realized the example I was using, sometimes if you have too many of the same number floating around, so what I'd like you to do is I'd like you to change example A so that it looks like that. It's just as easy, don't worry. So it's I want you to use x minus 1 quantity squared plus 4, and I want the interval to be from 0 to 2. So the first thing we're going to do on this is the hypothesis of the mean or of Rolle's theorem is important. So we want to make sure that, one, it's continuous on a closed interval, and that it's differentiable on the interior of that interval. So closed interval, that's easy to check. Is it continuous on that closed interval? Yeah, it's a polynomial function, so it's going to be continuous everywhere. And we know polynomials are nice and smooth and all that sort of stuff, so we know it's differentiable there also. Okay, so we've satisfied the hypothesis. Okay, if it does apply, then find the point or the points that are guaranteed to exist by Rolle's theorem. So here's what we want to check. We want to check and make sure that f of a is equal to f of b. So let's check f of 0. If I plug in a 0, I get -1. I square that, I add 4, so I get 5. So f of 0 is 5. F of 2, let's plug that in. 2 minus 1, that's 1 squared. That's going to be 1. Add 4, that's going to be 5 also. Have I made any arithmetic mistakes? Are we doing okay so far? Okay, so we've got taken care of right to that comma right there. We've got everything there. Okay. So then it says there's at least one number in that interval where the derivative will equal 0. Well, let's find the derivative. So let's find f prime of x. F prime of x is going to be 2. Leave the inside alone. Reduce the exponent. That's going to be a 1. So here's the derivative. Okay, now just a word. I normally just do this. Okay, if these two are the same, that means the average rate of change is equal to 0. And what I normally do is I normally just take the derivative, 2x minus 1, and I set that equal to 0. Okay, I don't put a c in there. Technically speaking, if you were to use this, what you should say is f prime of c is equal to 2 times c minus 1. Set 2 times c minus 1 equal to 0 and solve that. Okay, I don't really care. I normally just set the derivative equal to 0. Okay, take the derivative, set it equal to the average rate of change. Yeah. Yeah, and again, we're talking dummy variables here, so you could use anything you want. Okay. So if I solve this, here's what I end up with. I want to know when this equals 0. Well, that would happen when x equals 1, or using that dummy variable when c equals 1. Okay. So it just says, find the point or the points that are guaranteed. Well, I just found the number c, 1, whether you write it this way or this way, I don't really care, okay, where the derivative should equal 0. And this is a what one? This is a parabola. We can look at this and we can tell that that's where it would equal 0. So think about what this looks like. This is a parabola that opens up. The vertex is at 1, 4. And it hasn't been stretched or shrunk, so it looks something like this. The vertex is right here, and we only want the parabola from here to here, okay? So here's the average rate of change, and right there happens to be where the derivative, where the slope of the curve is also equal to 0. Average rate of change is 0. Average slope between the two endpoints is 0. Instantaneous slope, or the value of the derivative, is 0 there. Okay? So f prime of 1 is equal to 0. So here's where the instantaneous rate of change is equal to the average rate of change. There's just one point there. Okay? Any questions on that? Okay, let's take a look at the next one. Again, we want to make sure that we've satisfied the hypothesis of Rolle's theorem. So, first of all, is it continuous? Yes, it is. Okay, let's check the function value. So if I plug in a -1, this is really, what do we got here? We've got a 5th root of x squared. Would be an easy way to evaluate it. If I plug in a -1, I square that. That's a 1. Take the 5th root, I end up with a 1. If I find y of 1, if I plug in a 1, I get the same thing. So the function values at the endpoints are the same. So the average rate of change is going to be 0. Is it differentiable on that interval? Well, we can certainly find the derivative. That's going to be 2/5 x to the -3/5, which I'm going to write as 2, 5, 5th root of x cubed, right? Is that differentiable everywhere on that interval? Not at 0. So does Rolle's theorem apply? Rolle's theorem doesn't apply. That means something funky's got to happen in between there. The derivative doesn't exist at 0. What are the 3 ways a function can fail to exist? Cusp or corner, vertical tangent, Point of discontinuity. We already eliminated discontinuity because we said this was a continuous function. If you think about what this looks like, and I think we actually graphed this one before, this will look like a fifth root kind of here, but on this side, because of the squaring, it's going to go like that. Now, the function value here and here are the same, so the average rate of change is equal to 0. But because this isn't a nice, smooth, gently flowing, nice differentiable function, there's no point where the derivative will equal the average rate of change. All of these derivatives are negative. All of these derivatives are positive. There's nowhere where the derivative would equal 0. Good with that? Okay, so that's Rolle's theorem. And what we're going to do now is we're going to talk about the mean value theorem. The mean value theorem is much more useful. In fact, I've taught out of textbooks where they don't even talk about Rolle's theorem. Okay, Rolle's theorem is pretty easy to understand because if the two of these are the same, the average rate of change has got to be 0. 0 is a pretty easy number to work with. Well, the mean value theorem works like this. So we have to make sure that we've got a continuous function on a closed interval, and it's got to be differentiable on the interior. But then there's not that extra criteria that says the end function values have to be the same. F of b has to equal f of a. It just says then we're guaranteed there's at least one number in that interval where the derivative equals the average rate of change, no matter what the average rate of change is. Okay? So if we were to look at it over here, what we've done now is we've just allowed the endpoints to have different function values. So this right here is f of a, and this right here is f of b, and this is what the average rate of change would be. The average rate of change in this particular case, as I've drawn it here, has a positive value. It's got a positive slope, a positive rate of change between the two of those. It could be negative. It doesn't make any difference. Okay? As long as it's continuous and differentiable on that closed interval, then this says that the average rate of change is going to be equal to the instantaneous rate of change somewhere on there. And you can look at this and you can tell. These are really big positive slopes, relatively speaking. These are negative slopes. 0 would be about right here, but I would say that about right here, that looks okay. I would say that at about right there, we'll call that point C, then this is the instantaneous rate of change that equals that average rate of change right here. Slope of the tangent should be the same as the slope of the secant somewhere. And again, like we showed before, it's possible to have several places where it would equal that. So maybe something like this, about right here, about right here, about right there. Something like that, where all of those points have the same instantaneous rate of change or same derivative as the average rate of change. Okay? Now, this textbook uses a different, an alternate statement of the mean value theorem. The mean value theorem says that the derivative's got to be equal to the average rate of change at some point on that interval. How did they go from this statement right here, this equation right here, to this? Okay, they just multiplied by the denominator there. They got rid of that. Okay, now what I want you to think about is this. This means that the difference between the function values is related to the slope at that particular point, at this point right here, and how wide that interval is. Okay, so what we're doing here is we're saying you can figure out the difference between these two function values right here by knowing what the slope is and knowing how long the interval is. So if you tell me what the slope is and how far you want me to go, I can tell you how much difference in function values I'm going to accumulate. Okay? It's another way of verifying or checking the mean value theorem. Okay? It comes in handy sometimes. Honestly, I never saw that until I started teaching out of this textbook. Okay? So it's probably somebody's pet project to some extent. I will use that just so you can see how it would be used. So in words, this is what it means. The mean value theorem says that at some point on the interval, the instantaneous, the derivative must equal the average rate of change. Or in other words, the instantaneous rate of change must equal the average rate of change over that interval. It's kind of a restatement of Rolle's theorem, but Rolle's theorem, the average rate of change always had to be 0. Now we're saying the average rate of change can be anything we want. All right? So this has some really practical uses. So let's take a look at this example right here. It says a trucker turned in a ticket on the toll booth at a toll booth on the New Jersey Turnpike, showing that she had gone 160 miles in 2 hours. The speed limit on the turnpike is 75 miles per hour. The trucker was cited for speeding. Anybody been on a turnpike or a toll road before? Okay. Normally when you get on, so just like a freeway, so imagine getting on I-15, there's a toll booth to get on, or a little booth where you get a ticket. You get a ticket, and then when you get off, you have to go to a toll booth. Okay, right on the off-ramp, there's a toll booth. You give the person the ticket, they put it in a machine, and it tells you how much you owe based on how many miles you drove on that road. It's very common back east. We don't have them out here very much. Okay, but on there, it stamps what time you got on the road. So this trucker got a little stub out of the machine when they got on. 2 hours later, at a toll booth that's 160 miles away, turned it in, and they said, okay, that's going to be $15 for using our road, and by the way, you have a $150 ticket for speeding. Okay, how can you tell from the information that they were speeding? One, they went 160 miles in 2 hours. 160 miles in 2 hours is 80 miles per hour. Now, that's an average rate of change. Okay, you know what the time difference was, and you know the distance difference. Okay, so miles on top, hours on the bottom. 160 miles on top, 2 hours on the bottom. The average rate of change was 80 miles per hour. If the speed limit is 70 miles per hour, the mean value theorem says somewhere in between there, that person had to be going at least 80 miles per hour. Okay, now in fact, if you think about it, wouldn't this truck driver had to have been going more than 80 miles per hour? Yeah, because what would happen is you'd start out really slow, speed up, go really fast for a long time, and then you'd have to slow down. Okay, and 80 miles per hour is probably about right there. Okay, so there were probably 2 times they were going 80, according to the mean value theorem. Okay, and we'll talk more about that idea a little bit later. Does that idea make sense? If the average was 80, somewhere in between there, they had to be going at least 80. Okay? There had to be one time when they were going 80. At least one time. Okay? Any questions? Okay. Let's flip the page over and let's do some actual math problems with this. Okay, example 3 says, determine whether the mean value theorem applies on the closed interval. If it does, find the point or points that are guaranteed to exist by the mean value theorem. Then sketch the function on the interval along with the secant line and the tangent lines found using the mean value theorem. So, real easy function to start off with. Let's see, did I change this one at all? I don't think so. I think that's the way it was. So, first thing we want to check is it continuous? Yes. Closed interval? Yes. Differentiable on the interior? Yes. Okay? So, here's what we want to do. Let's find f of 0. F of 0 is 0. Let's find f of 2. F of 2 is 4. Let's find the average rate of change. The average rate of change would be 4 minus 0 over 2 minus 0. F of b minus f of a over b minus a. Let's find the derivative. The derivative is 2x. Now, again, this is where you could put a c in here if you want. If you want to put a 2x here, that's fine. If you want to put a 2c here, that's fine. So 2 times c should equal, well, this is just 4 over 2, so that's 2. So what's c? C equals 1. Okay? So if I draw a picture of this, so let's try and draw it reasonably accurately. So I'm going to draw the scale like that. It goes through 0, 0, and 1, 1, and 4, 2. So here's what it looks like. There's the parabola. Then the average rate of change would be the secant line between the 2 endpoints. So that's going to be from here to here. You can look at it and you can see that the slope is 2, along with our calculation right here. And then if we look at this, right here we have a slope of 0. Right here we have a slope of 4. Right about there, it looks like that would be the place where the secant line and the tangent line would have exactly the same slope. Okay? So f prime of 1 is equal to 2. This is the instantaneous rate of change, and it equals the average rate of change right there. Make sense? Okay. Let's take a look at the next one. Continuous on this interval right here. You can plug in the endpoints, okay, and you can plug in, these are small numbers between -1 and +1, so this is going to exist. We're not going to have the danger of taking a square root of a negative. By the way, does anybody know what this looks like? 1050 coming back to haunt you. This is a circle, top half of a circle centered at the origin, okay? It's got a radius of 1. So it looks like this. It's differentiable. If you find the derivative, let's go ahead and do that first on this one. This is going to be 1 over 2 square root 1 minus x squared. That's the derivative of the outside, left the inside alone. Then times negative 2x. With me there? So I can cancel that. So the derivative is negative x over square root 1 minus x squared. Is it differentiable on the interior of this? Yeah, you can't plug in any numbers that are bigger than 1 or less than -1. Can't be taking the square root of a negative. And you can't even plug in the endpoints because the derivative or the value of the denominator would be 0. The derivative wouldn't exist. Okay? But we're okay. Yeah, we'd have vertical tangents on the endpoints here. Okay? But it is differentiable everywhere in between. Okay? Let's check the function values. What's f of -1 and what's f of +1? If you plug in a -1, you get 0, and that happens to be the same thing as if you get a positive one. So the function values in both cases are 0. Then what's the average rate of change? Average rate of change is 0. So there's the average rate of change. And again, what the mean value theorem does is it relates the instantaneous rate of change, it relates the derivative to the average rate of change. So the derivative is negative x over square root 1 minus x squared, and the average rate of change is 0. Well, when do these two things equal each other? When x is 0. So that's the point guaranteed to exist by the mean value theorem, and let's just draw a picture of it, because it said draw the tangent line. The tangent line at 0 is this tangent line, and the secant line is this secant line, whoops, right here. And they have the same slope, okay? More specifically, this is another example of Rolle's theorem, okay? But you can just think of it all as the mean value theorem. Any questions there? Okay, let's do one that's a little bit less familiar. It says f of x is ln of x, and the interval is the closed interval from 1 to e. From 1 to e. Closed interval, that's good. That's a continuous function everywhere where it's defined. I mean, it's just that kind of shape like this. So it's continuous. We're in good shape there. Is it differentiable everywhere there? Well, let's find the derivative. The derivative is 1 over x. The only thing you can't plug into this is 0, and we're plugging in all positive values, so it's continuous and it's differentiable. We're in good shape there. Any questions? Okay. I've got the instantaneous rate of change that I can use for comparison. Now I need to find the average rate of change. So let's find the average rate of change. Let's find f of 1 and let's find f of e. If I plug a 1 in, I get 0. If I plug an e in, I get 1. So if I do f of b minus f of a over b minus a on this particular problem, I'm going to have 1 minus 0 over e minus 1. Is that right? This is a, this is b. So here's the average rate of change. 1 over e minus 1. So again, this is the instantaneous rate of change. So I'm trying to have you look at this in several different ways. This is the average rate of change. What does the mean value say, or the mean value theorem say? Yep, says there's at least one point where those two things ought to be the same. So let's set them equal to each other. Let's have 1 over x equal to 1 over e minus 1. Now, when would that be true? When x equals e minus 1. Okay? That is the point that's guaranteed to exist by the mean value theorem. Okay? Don't need to do anything complicated this. If you wanted to do cross multiplication and solve the equation, stuff like that, you'd still get e minus 1, right? Okay. Any questions? Okay, let's take a look at what the graph looks like. I'm going to blow this up just a little bit. So ln looks like this. This point right here is 1, comma 0. Okay, and if that's 1, this would be 2, and this would be 3. So we'd be, so let me draw this a little bit. At 2.71 at e, it's got to go through 1. So let's make it look like this. And that point right there is e, comma 1. So here's the secant line. The secant looks like that. And we just said that the average rate of change should equal the instantaneous rate of change at e minus 1. Well, e minus 1 would be about 1.7, right? So 1.7 would be about right here. So let's go here. Now, this is just a sketch, but does it look okay? Does it look like the instantaneous rate of change? The derivative there would equal the average rate of change? Not too bad, right? Okay. Any questions? Okay. I do want to show you one use of this guy right here. We're going to use that little statement right here that the difference between the function values should be related to the slope at that point found by the mean value theorem times the difference between the x values. Okay? And let's just use this to verify, just to show that this does indeed work. So this would be f of e minus f of 1 should be equal to the derivative at that point. The derivative at that point was 1 over e minus 1. Average rate of change and instantaneous rate of change were the same. They both had a slope of 1 over e minus 1. And then this is times e minus 1. B in this case is e. A in this case is 1. So e minus 1 here. F of e, f of 1. Everybody good there? Let's take care of this side first. What's 1 over e minus 1 times e minus 1? 1. What's f of e? What did we get when we plugged in an e? We got a 1 minus f of 1, 0. 1 minus 0 equals 1. Check. That works. Okay. Any questions? Okay. So it's kind of interesting that the average rate of change will equal the instantaneous rate of change somewhere. We can have some nice uses for that. But the main use for the mean value theorem for derivatives is what's coming up next. And this is a very critical idea. Okay? And this kind of starts laying the foundation for what we're going to study for the rest of this semester. So here's the statement here. And this is a consequence of the mean value theorem. It says functions with 0 for a derivative are constant functions. Functions with 0 for a derivative are constant functions. Okay? And we can prove this using the mean value theorem. So what it says is, if the derivative is 0 for all x's in an interval from a to b, then that function has to be equal to a constant for all of the values in that interval from a to b. So the proof of this is very simple. It just uses the mean value theorem, a very simple statement. This is the mean value theorem. Just says the instantaneous rate of change, the derivative has to equal the average rate of change. Okay? So if the derivative is 0 then just replace this side with a 0. So the derivative is always 0. Well, if I've got an equation now that's got a 0 on this side and a rational expression on this side, a fraction on this side, what's the only part of this fraction that can make the whole thing equal to 0? Just the numerator, right? Okay? So what this means is 0 would have to equal f of b minus f of a. And the only way that can happen, I'll move the f of a to the other side, is if f of a is equal to f of b. And since it doesn't matter what choice we have for a and b, we can choose any points a and b for the particular function. The mean value theorem better be true. So what this says is no matter what points you pick for a and b, the function values are all the same for any a and b. So if it's for any a and b, that means they've all got to be the same. They all have to be equal to each other. So let's take a look at an example or an application of this. Suppose I tell you that the derivative is 0 everywhere and f of 4 is equal to 2. What's the original function? What is f of x? Well, let's think about this for just a second. What we're saying here is the derivative is equal to 0. That means it's a flat line everywhere. It's a flat line everywhere, and I'm telling you that at 4, it goes through 2. Well, if it's a flat line everywhere and it happens to go through 2, if one of the function values is 2, then all the function values have to be 2. So just like up here where we said, well, gosh, if the derivative is always 0, then the function values always have to be equal to each other. So the original function must have been a constant. Here I'm telling you the derivative is 0 everywhere. I'm giving you a point that it goes through. If it goes through 4, 2, then all of them have to have a function value of 2, so f of x has to be 2. Okay, so stop and think about that for just a second. This is the first time where we've done the opposite of differentiating. We're always used to taking a function and finding the derivatives. First derivative, second derivative, third derivative, so forth. Got position, I can find velocity. Got velocity, I can find acceleration. What we just did is I told you what the derivative was, and we went backwards and figured out what the original function was. Granted, this is a very easy example. Okay? But that idea is very powerful, and that's what we're going to spend some time doing in some of these other sections. So at the bottom of the page, it's got a few problems where it says find the derivative, and these are all very easy. So if y is equal to x squared, y prime is 2x. If y is equal to x squared plus 1, y prime is equal to 2x. If w is equal to 1/5 e to the 5x minus 4, the derivative is e to the 5x. And if instead of adding or subtracting 4, I add 100, still e to the 5x. Derivative of cosine, negative sine, negative sine. What's this one? Cosine 2x. And this one? As ugly as that number is, this is still cosine of 2x. Okay? Now, if you flip over the page, I'm going to leave the bottom of that page available there so we can look at it. So these kind of came in sets of functions and sets of derivatives. Okay? And each set of similar functions had exactly the same derivative. It didn't matter if this was a 0 and that was a 1, or this was a negative 12 and this was a negative e to the 12th. The derivative was exactly the same. Derivatives were the same for each one of those pairs of functions. Okay? Even though the original function was just slightly different. Okay? The original functions differed by a constant. The original functions were different by a constant. Maybe a pretty big constant, Maybe not that big a difference, but they all differed by a constant. Okay? And that leads us to another consequence of the mean value theorem, and that's this. Functions with the same derivative differ by a constant. Functions with the same derivative differ by a constant. So, if the derivative of f and the derivative of g are the same for all the x's in a particular interval, then f of x is exactly the same as g of x, give or take a constant. So we've got this thing that we call an arbitrary constant. If they have the same derivative, then they've got to have the same function to begin with, plus or minus a constant. Okay? Give or take a constant. So if I were to name three functions, all of whom have a derivative of 2x, got to have an x squared plus 400. That would have a derivative of 2x. X squared minus 17. X squared, I could put some big ugly number here, 4 to the 27th. Every one of those, regardless of what the constant is, has exactly the same derivative. Every one of them has a derivative of 2x. Now, can anybody explain why that's true? Why is that theorem true? Okay, the derivative of a constant is 0. All by that. So the derivative of every one of those is 0. Okay, but think about what the graphs look like. Yeah. Okay, that's the big idea there. Whether we move this up to 400, down to 17, so the original starting shape is that parabola. If I slide it up to 400, down to 17, or up to whatever 4 to the 27th is, that's not going to change what the slopes are at a particular point. So if I go to 1, the slope here is going to be 2. It's going to be 2 on every one of these. Okay? Because the derivative keeps track of slopes, not function values. Okay? The derivative only keeps track of slopes, not function values. And that's why they can differ by a constant. Okay. And we'll use that again. Well, that'll come up in section 4.9 and a lot in chapter 5. But for right now, just kind of have that in your head, have that cooking there. I've got 2 more problems to look at, and I will warn you, these are a little bit wild. These are not things that I would ask on a test, but they are interesting thought questions and interesting consequences of some of these theorems. And what's fascinating about this is there's always more than one way to do something, and it's also fascinating how everything just kind of fits together. So I'm going to show you how to do problem number 20 and problem number 33. Okay, so problem number 20 says, and if you just want to watch, you don't have to write this down. If you want me to email the last page of this to you, I will. Okay, so it says, show that the equation x to the 4th plus 4x plus c equals 0 has at most 2 real zeros. Okay, and the way we're going to do this is we're going to do something called proof by contradiction. Okay, so proof by contradiction works like this. Assume that in this case it says at most 2 real zeros. So let's just assume there are more. And then let's follow that through and let's find that there has to be a contradiction here. Okay? So what we're going to do is we're going to say, take this function right here and suppose it has 3 distinct real zeros, and we're going to call them p, q, and r. So this one says it has at most 2 real roots, or real zeros, or x-intercepts, or however you want to talk about it. Let's assume there are 3. So what that means is, if each one of those is a root or a 0, that means f of p, f of q, and f of r are all equal to 0, because they'd be on the x-axis, right? Okay, so by Rolle's theorem, we can conclude this. Between p and q, okay, we're going to call it an x1. So there's got to be a point between p and q where the derivative would equal 0. Since all of these are equal to 0, the average rate of change between there would be equal to 0. So there's got to be a point between the 2 of those where the derivative equals 0. Yeah. It's going to have 4 roots. Two of them would be imaginary and 2 would be real. Yeah, that's and yeah, and that so we could do that as a contradiction as well. So you see what Juan's saying? He's saying if you're going to say there's 3, there's got to be 4 because you can't have an imaginary one show up as just a single. They've always got to come in pairs. Okay, but we want to use calculus to do that. Great pre-calculus technique. We want to use calculus here. Okay. So in between P and Q, there's got to be one where the derivative equals 0. And in between Q and R, there's got to be another one where the derivative equals 0. Oops, that's a 2 equals 0. And that's a 2. Everybody good with that? Okay, so let's find the derivative. The derivative would be 4x to the third plus 4, right? There have got to be 2 places. Given this assumption, there have got to be 2 places where the derivative equals 0, correct? So we want to know when does that equal 0. So let's start solving that. I had somebody come to me earlier today and say, you know, that 1050 pre-calculus stuff is kicking my butt. Okay, because we're now using the derivative, finding derivatives relatively quickly, hopefully. But then you have to do something with them. You've got to solve a problem, and most of it involves some algebra and some trig. So when we get to this point right here, does anybody remember how to solve this? The easiest way to solve this is by factoring. There's no, well, there is a cubic formula, but you wouldn't want to use it. This does factor. This is a sum of cubes. This is a perfect cube of x, and that's a perfect cube of 1. So this factors to x plus 1. And then we're going to have x squared minus x plus 1. So this would equal 0 when x is equal to negative 1. So I've got one of the solutions that comes from this. But then there are 2 more right here. But let's take a look at what we end up with. Okay, we've assumed that there are going to be 3 real zeros, 3 real roots. Okay, let's see what we get here. I have to solve this using the quadratic formula. This is going to be 1 plus or minus. Let's see, that's going to be 1 minus 4 times a times c. A and c are both 1, and that's all over 2. And right here is the problem. What's going to be underneath the radical? Negative 3. So, are these going to be real solutions or imaginary solutions? Okay, so these are going to be imaginary. So what we've done here is we've said, look, if there are 3 real zeros, then there are going to be 2 places where the derivative, because if let's say it looks like this, there are going to be 2 places where the derivative would have to equal 0. 2 real numbers where the derivative would have to equal 0. Well, if I go through and I find when the derivative equals 0, I only get 1 real number where the derivative equals 0. So this must not be true. So by contradiction, there's got to be at most 2 real zeros. There can't be 3. Got to only be 2. Chew on that for a while. Wouldn't ask you a test question. But it's an interesting application of the mean value theorem, because when I assume that it crosses the x-axis in 3 places, that means I know for a fact, or one of the extensions of that would have to be that the derivative would have to equal 0 at least twice. Make sense? 1 between these 2 and 1 between these 2. Okay? All right. This one is kind of interesting. This is problem number 33. It says, prove the identity. What on earth would that trig, inverse trig identity, have to do with calculus at all? Okay, well, think back to when you were verifying trig identities. They are pretty much a pain. And this, I would guess, I mean, it's the ugliest identity that I've seen to verify. And doing it using trigonometry might be very, very difficult. Because remember, you want to work on the complicated side, usually work on one side, manipulate it until it looks like the other side. That would be a huge pain in the butt. Okay? So there's an example on page 288 of how you can do this. Okay? And this is how it would work. If these two things are equal, okay? So again, you can just watch, and if you watch and listen, and if you want me to email you this page so you don't have to write anything down, I'm happy to do that. Okay? If these two things are equal, what would happen if I moved both of them on the same side? What would this equation turn into? It would turn into 0, okay? So if equal, then I'm going to move them on the same side. Then I'd have sine inverse of x minus 1 over x plus 1 minus 2 tangent inverse of square root x. And that looks ugly, but the derivative is actually pretty easy to find. Okay? Then that would have to equal 0. And I'm going to put an f of x here no matter what I plug in. Okay? Because that's what it means to have an identity. When these two sides are defined, and no matter what number I plug in, the two sides would have to be equal. So if I move it on the same side, this should be equal to 0 no matter what number I plug in. So I'm going to deal with this function right here. So one thing I could do to kind of help out is, let's see if we could get it to work for a number. Any number. Well, take a good look at this. Right? I think the easiest number to plug in would probably be a 1. Probably a 1. So let's check and see what f of 1 is. Let's see if it does actually equal 0 somewhere. So if I plug in a 1, I get the sine inverse of, this would be, well, that would be a 0. That's good. Then I get minus 2 times the tangent inverse of, if I plug in a 1 here, I get a 1, and then plus pi halves. Now, what I'm hoping is, if I go through and simplify this, I'm hoping that I get a 0. I hope it actually does go through 0. So then it's an identity for at least 1 point. It's a true equation for at least 1 point. So sine inverse of 0. Sine inverse of 0 would be 0. Okay? Tangent inverse of 1, let's think about that. Tangent inverse of 1, that's 1 over 1, ratio of the opposite side over the adjacent side. So that's going to be pi fourths. So this is a negative 2 times pi fourths plus pi halves. So this is going to be negative pi halves plus pi halves, so that equals 0. So f of 1 at least equals 0. Okay? So these two sides would be equal if you plugged in a 1. Okay, now, come back up here. Remember this one right here? Okay, I just told you the equivalent of saying that I've got a function value of function value of 2 at 4. So we just figured out if you plug in a 1, you get a 0. So what we just figured out is if you plug in a 1, you get out a 0. I want this whole thing to always be equal to 0. I've got a point where it's equal to 0. I want the whole thing to be equal to 0. How could I prove that the whole thing is equal to 0? That function is always equal to 0. If I've got one point that's equal to 0, how could I make sure that all the other points are equal to 0? And we're in calculus and we've been finding derivatives. Yeah, prove that the slope is always 0. So find f prime and show that it equals to 0, and you're done. Now, as ugly as this is, it actually works out to be not too terribly bad. And guess what the derivative is? The derivative is 0. It doesn't look like this could ever possibly be equal to 0. But if I do, let's see, this would be 1 over big square root 1 minus that squared. times the derivative using the quotient rule. So I'm going to have an x plus 1 quantity squared here. I'm going to have the bottom times the derivative of the top minus the top times, whoops, that should be a minus the top times the derivative of the bottom, all over the bottom squared. And then the derivative of tangent inverse, that's going to be minus 2, 1 over 1 plus, this is kind of cool, square root of x squared. And what's the derivative of square root of x? 1 over 2 square root of x. And what's the derivative of pi halves? 0. Guess what you get if you simplify that? Doesn't look like it, but you get a 0. Okay? Yeah, that square root x squared is going to be x. Yeah, I just showed all the work. I'm not done. I don't have time to finish it. But if you did simplify this ugly mess, doesn't look like it would be 0, but lo and behold, it is 0. Okay? The graph is just the graph of this function right here is just a straight line at 0, which means these two things must equal each other. Okay? Think about, so let me ease your mind. Again, am I going to ask a question like this on the test? Probably not. Okay? But this should be kind of interesting, and if you think about it for a while, you should be able to put the pieces together. Okay? All right. That's it for today. Thank you very much.